Hi, this is Matthew Sherland, and this is part 2 of my video description for the Simulink PV Array Boost Converter and Grid-Tied Inverter project. In part 1, we talked about the PV Array, Boost Converter, and the MPPT controller. And this part we'll be going over the DC to AC inverter, its connection to the utility grid, as well as the VSC control for the inverter. Our inverter uses a 3-level bridge, and that allows for 3 outputs corresponding to 3 different phases for our voltage, A, B, and C phase, so that when it hits the utility grid, there's 3-phase power going to the grid. It has an RL load here that's used to simulate the natural inductance and resistance of the transmission lines used for this kind of system. It also has a resistive capacitive component here. This is used to help filter out harmonics, improving the quality of the voltage and current signals. Now, our 3-level bridge uses diodes and IGBTs as the semiconductor components for it. One peculiar thing about this, as to similar with the boost converter, these were programmed to have 0 volts for the voltage drop. However, realistically, there would be some kind of finite forward voltage drop as a signal is put through them. Silicon, it'd be around 0.7 volts you would see as a drop. Now, with it using IGBTs, one advantageous thing about that is that you can control both the on and off time for when the IGBT operates. This is more advantageous than using a thyristor, which you can only control the on time. One useful thing about this is that it could allow for voltage amplitude modulation. Now, this VSC control here, this controls the pulse width modulated signals that are used to trigger the gate of each IGBT. That gate signal controls when the IGBT is both on and off. So we can see here that we have around 500 volts input into that DC, and we want to convert it to around 260 volts RMS AC here, which is what the transformer is designed for. Now, voltage amplitude modulation would allow for this by controlling the amount of time during the period that the output signal is actually seeing the 500 volt input signal, and that's used by adjusting the firing angle from the pulse width modulated signals to the IGBT's gates. By controlling when it's on and off using those firing angles, we can get the output signal to be 260 volts RMS. We can see that here using the output waveform for it. Now, as we can see, that it successfully turned a DC signal into a mostly sinusoidal AC signal. This signal has a peak amplitude around 370 volts. The RMS voltage for that is 261 volts. So as we can see, we got it to successfully drop down to our targeted 260 volts RMS using the VSC control to adjust the firing angles. This 260 volts is stepped up to 25 kilovolts through a transformer and sent out to utility grid for a high voltage power transmission. One advantageous thing about this is by significantly increasing the voltage, you are significantly decreasing the current. This reduces power losses as it is transmitted through the wires of the utility grid. The output power that we got for our whole system hitting the utility grid is 91.29 kilowatts, where our input power coming from the PV array was 92.89 kilowatts. This provides our whole system with an efficiency of over 98%. Now, this high efficiency percentage just stresses the need further for having MPPT controllers for larger solar array systems. This allows the system to constantly be operating at or near the maximum power point. Without such a controller, you would be unable to control the power point that the system was operating at, and thus a lot of the power coming from the PV array would be lost, the efficiency would decrease, and this output power would be a lot less. That was the second part of my video description. There will be a detailed written description along with this uploaded to Canvas as part of this project. Thank you very much.